Okay, so we're beginning Unit 3, which picks up kind of at the end of Chapter 5. So we're still going to go through a couple more sections in Chapter 5, starting with fitting exponential functions to data. Okay, so let's look at an example here. This is population data beginning in 1790 and going forward every 10 years, population in millions from the U.S. Census. Okay, so graphing or plotting a little bit more about this data, we've got the initial years, then we've got the years after 1790, the populations, and then this last column we've just added the average rates of change. And what you can see from the average rates of change is that they are positive and increasing. Okay, so that's going to be a concave up graph, and it looks like an exponential function would be a reasonable candidate model. But just as we've done for linear functions, we want to find the best exponential model. In other words, looking at this data, it may be that this is roughly exponential, but not perfectly exponential. And so then the question becomes, what's the best exponential function to model the data? And no surprise, just as we did in the linear modeling's portion of the class, the best exponential model to a given data set is in fact the one from exponential regression. And we already know how to do this because we have been using exponential regression quite a bit in the previous unit, so I assume everybody knows where it is now. The only difference now is that we're going to be using it for sort of its proper application, which is for approximating lots of data. Okay. So if you do exponential regression with this data, you will get a function of this form. 3.9396 is your initial value, and then a factor of 1.03, and store that as y1. I don't think that this needs a whole lot of explanation, just considering the experience that you should already have using exponential regression. But nevertheless, to do this, the difference now is that rather than just having 2 points, we're going to have a whole set of points. And as we did for linear regression, we put the elapsed time in the L1 column, and then we put our populations in the L2 column. And then depending on what type of calculator you have, when you choose exponential regression, you'll either have this screen down here or you'll have this screen, one of these two. But in either case, you should end up with an exponential function that looks like the following. Okay. So a couple of things about this. The growth factor, this is a increasing function, so it has a growth factor, not a decay factor. That's the growth factor B. And this latter portion, the 0.03, etc., that's your growth rate, and that's calculated down here. And let me just write factor here. So that's the factor. All of that is the factor. And this is the rate. So we just subtract 1 from the factor, as usual, multiply by 100 to get it in percent form. So 3% growth rate. We can also perform an error analysis just as we've done for the linear regression functions. And what that means is that an error analysis consists of, for us anyway, consists of calculating the SSE and the average error, maybe the correlation coefficient, the model error, the percent error, and so forth. But we begin with the SSE and the average error. The nice thing about these is the method of calculation is exactly the same as it was for linear regression. We can just, once we've done the regression, we can go to the regular calculation screen, enter sum, resid squared, and then that will give you your SSE. And then to calculate the average error, we take the answer from the SSE, divide it by the number of data points, which in this case is 6, and then take the square root of all that, and that's 0.084. Okay, so it's a nice and easy jump from linear regression to exponential regression. Pretty much all the things that we did before, we still do them now, including the correlation coefficient. So we can find the exponential correlation coefficient for this set of data, and it's very close to 1, 0.999, and this is located in the same place as it is for linear regression. Go to variable statistics. Oh, well, let me pull up the calculator. Variables, statistics, equation, and number 7. I haven't actually entered the function yet, but number 7 is that would give you your correlation coefficient. As usual, when we are looking at a correlation coefficient, we actually want to check and make sure that it is high enough to be 95% positive in correlation. And to do that, we look at the critical value. We use the same critical value table that we used for linear regression. Those are the critical values for 95% confidence. And the original table is located back in the notes for, I believe that was Unit 2. Actually, it might have been Unit 1. I'm not sure off the top of my head, but we had that big table. I probably will pull that out and make a separate document with just that table so you have easy reference to it. But in any case, we look up the critical value that corresponds to n equals 6, and that's 0.811. And our test for correlation is the same as it was for linear regression. We compare the absolute value of the correlation coefficient to the critical value, and if its absolute value exceeds the critical value, then we can be 95% certain in correlation, and in this case, that would be positive correlation. And one little note, I know that R is the letter that's used in the calculator for correlation coefficient, and we've used that before as well. But in Units 2 and 3, since we've got exponential modeling happening and we use R to represent the growth rate all the time, it's easy to get confused. So we're going to use CC for correlation coefficient. Okay, there's a graph of the model. Looks pretty good. All right, let's talk a little bit about using this model for some things. Find the U.S. population's annual percentage increase. So this is, we actually already did this, and this is an important thing, is if you can recognize, when you see a question like this asking you for the percentage increase or the percentage decrease, that's just asking for the rate. In this case, that's the growth rate. So this is just another way of saying what is the growth rate for your model. And we already found it when we did the regression. We go back. There it is right there, 3%. So we've already got our growth rate. Okay. So we can move on to question B. Predict the U.S. population in 1850, 1860, and 1870. So these are just... well, let's see, when did our model end? Our model, the last date of our model was 1840, and 1840, okay, so that means we are going to be extrapolating. In other words, we are going to be predicting the future, or attempting to predict the future with our model. And we're in every one of these, the procedure is going to be the same. You would go to vars, yvars, find your function, and then you would evaluate y1 for 18. I keep forgetting when we actually started the model. So 1790. Okay, 1790. So 1790 is when we started. So you can just type in 1850 minus 1790 if you don't want to do the arithmetic in the parentheses, or that's just 60. So you could just type in 60 and then evaluate that, and then do it again for 1860 and 1870. Okay. Oops, and I've gone too far. Here are your answers for evaluating the model at these three inputs: 23.22, 31.20, and 41.93. So that's what you should get for those three. And I think the next question, we actually have the actual values for these dates, and we're going to compare the model to the actual values. So the actual population well, I have misplaced the slide. Where is it? There it is. 23.2, 31.4, and 38.6. Okay, so the issue here, 31.4 and 38.6, so the actual especially this last one, the model predicts 41, the actual population was 38. The thing that happened during this time period was the Civil War, and so population growth was slowed during that time period. To compute the model errors, it's the same, and the percent errors is the same computation as always. That's actual minus predicted divided, this is for percent error, actual minus predicted divided by the actual value, and then multiply that by 100. Okay. So I think I'll stop this video now, and we'll pick up the next one and do this next example.